welcome to the next episode of my science podcast. Today I am delighted to welcome Professor Dejan Stojkovic, who is a professor in the Department of Physics at Buffalo University and the author of the book Massive Neutrinos and Topology of the Standard Model, Cosmic Strings, Domain Walls and Index Theorems. In March 2012, he was awarded with the Marko Jaric Award, which is known as the Serbian Nobel Prize in Physics. And his areas of interest include cosmology, gravity, particle physics, black holes, extra dimensions, and much more. So thank you so much for joining me today.
Thank you very much for inviting me. It's my pleasure.
So to start off with, may you tell us a bit about your career and research?
Well, I was born in Serbia. At that time, it was called Yugoslavia, former Yugoslavia. And there, almost by a rule, half of my professors were educated in the East and half of them in the West. My Bachelor of Science thesis advisor was educated in UK. Actually, he got his PhD there. My Masters of Science thesis advisor was educated in the United States. But I had many professors. For example, a professor who taught me electromagnetism, he was Landau's student in former Soviet Union. So I try to pick up, to absorb the best things from both of these worlds and to use them to my advantage. So I noticed, for example, that in the East, you get much broader education. The accent is put on concepts and ideas, while in the West, education is a little bit more narrow. So you get your specialized education, you become the best in the world just in your narrow field of expertise. But the accent is put on practical problems which have connection with everyday life. So I try to use both of these things, combine them together. So after I absorbed everything I could absorb in Serbia, I moved to US. So I got my PhD at Case Western Reserve University in Cleveland. So after my PhD, I did two postdoctoral positions, one University of Alberta, another one at University of Michigan, Ann Arbor. After that, I got my professorship at the State University of New York in Buffalo, and then I stayed there ever since. So that's my short career path. And, about the research, I do research in high energy physics broadly defined. So by that I mean particle physics, gravity, cosmology, and mostly the topics which are on the interface between these seemingly different areas, but they are actually very tightly connected. So I work on fundamental problems in these areas. Why, if you really ask me, I mean, since I was aware of myself when I was a kid, maybe 4 or 5 years old, I remember myself looking at the star or at the sky, night sky, full of stars. And I was thinking, wow, what is all this? But then I looked down at myself and who am I and what am I doing here? So I really entered physics and science to understand the world around me, to see what is all this about, including myself. So that's basically the motivation to start doing what I'm doing, and I never stopped.
Amazing. So we're going to jump straight in. So do you believe that wormholes exist and why?
So you can't say with certainty. So you can't say, okay, I'm 100% sure that wormholes exist. But there is a good chance that they exist. Why? Because they're exact solutions of Einstein's equations of general relativity. General relativity is a theory of gravity. So they are not just like a figment of our imagination or some constructs which are heavily explored in science fiction. They are actually exact solution to Einstein's equations. And as far as I can say, whatever is not explicitly forbidden by some principle, nature finds a way to make it somewhere out there. So as such, I believe there is a good chance that wormholes exist.
Exactly. Scientists have been spending decades on this, trying to disprove them, and haven't really got anywhere. So Perhaps they do exist. So how could we go about observing a wormhole?
So there are several ways. One of the ways that I used in my papers is the very fact that if a wormhole is traversable, that means if you can go from one side to another, then if I can go through it, or spaceships, then electromagnetic and gravitational fields can go too. Which is what? If there is a wormhole and I'm observing, for example, an orbit of a star on my side of the universe, then if by any chance there is something on the other side, another heavy star or another black hole or whatever, then gravitational perturbations can go through the wormhole and perturb the motion of the star on my side. So if I observe very precisely the motion of a star on my side, and I see some unexplained perturbations, so I see that motion deviates from my predictions, and I don't see anything else that can perturb the motion, it's very likely that the perturbation comes from the other side of the wormhole. So that's one way. Another way is the fact that to stabilize the wormhole, you need a negative energy density, which is going to provide the repulsive gravity and prevent the throat of the wormhole to collapse under its own gravity. But negative energy density, exactly because of the reason I mentioned, has exactly the opposite properties from matter with positive energy density.
Yeah.
So it provides repulsive force. So now if you have any light ray propagating in the vicinity of some concentration of negative energy, then instead of focusing, you have defocusing. So it's repulsive gravity. So you are going to change everything. You are going to change gravitational lensing, might change propagation of gravitational waves. You might change the dynamics of the accretion disk. So basically, you use these two facts to observe a potential wormhole candidate in our universe.
And physicists are looking at the star S2, which is around Sagittarius A, which is the supermassive black hole at the center of the Milky Way, which is possibly a wormhole. Could you tell us a bit about this?
Yeah, that's the paper that we wrote, and it got a lot of attention. So we just used it as an example. We didn't say the center of our galaxy is a wormhole. We said if it was a wormhole, how to test it. And then we used the star that you mentioned. We followed the motion of that star for 20 years. So we mapped it pretty well. We mapped one full orbit and a little bit more. And then we said, okay, if Sagittarius A star is a wormhole, so if there is something on the other side that perturbs the motion of S2, then when can we tell if the center of our universe is a wormhole or not? So with the precision that we have right now, we still don't know the motion of S2 precisely enough. So with the current precision, you can exclude only very heavy objects that possibly exist on the other side, like another supermassive black holes with millions of solar masses. But you can't exclude, for example, solar mass objects on the other side. When the precision reaches a certain level that we expect to get within a decade or so, then if we don't see any suspicious perturbations of the motion of S2, then we can exclude even generic objects of solar mass. Once you exclude that, then you can say most likely the center of our galaxy is not a wormhole. If we observe any deviation from motion, then the interesting things will start. Then you have to model the motion much better, because there is maybe something very dim on our side, some other black hole or neutron star, which we cannot see so clearly, but it perturbs the motion of S2 from our side. So it's still not a wormhole. So after you do a complete modeling and exclude all of the other more natural explanations, and if there is nothing left, then you have to accept. I mean, when you exclude everything, that's impossible, that the only remaining possibility, no matter how unlikely, is probably the correct explanation.
Absolutely. So do you think that humanity will ever be advanced enough to make a man-made wormhole?
I'm an optimist. So I would say, okay, but let me first make distinction between small microscopic wormholes. These are much more likely to be made in the lab by humans. I would say, okay, maybe I'm going to be too optimistic, 50 to 100 years. Because as I said, the main problem is the negative energy density and how to stabilize the wormhole. But in quantum mechanics, we do know that we have negative energy densities all over the place.
Yeah.
We have Casimir effect, for example, which demonstrates explicitly that you can have negative energy. Microscopic, so small amounts of negative energy are much easier to produce in a controlled experiment than big macroscopic amounts that require large wormholes, I mean, so that we as people or spaceships can pass through. So small ones are more likely to be produced by humans, maybe, as I said, 50 to 100 years. Big ones, I believe in even that. We have to change our technology radically, of course. And probably we have to change even our understanding of space and time, because by using a wormhole, you're practically manipulating space-time itself. So before you learn how to manipulate the space-time, you have to understand what space-time is. But we still have quantum theory of gravity. But I'm pretty sure that, I don't know, maybe I'm again optimistic. Let's say in 500 years, we will be able to make big wormholes, wormholes that we can go through.
Amazing. So what kinds, you've touched on this a little bit, but what kinds of exotic matter could we use to keep the wormhole throat open? So you've touched on the Casimir effect. Can you expand upon this a bit?
Casimir effect is an explanation. I mean, it's a very nice demonstration of the existence of energy states which are less than zero, which are practically negative. It requires a little bit of lingo, so let me do it as simple as possible. So vacuum, what we consider vacuum classically is not really vacuum. It's not really empty space. So classically, if you take certain volume and take out all of the particles from it, so there's nothing there, you call that vacuum, and that's your lowest energy state. And you say that's energy zero state. There's nothing there. But quantum mechanics teaches us that's not quite true, because even in that empty space, you have quantum fluctuations. So you have particles popping in and out of existence all the time, in accordance with the Heisenberg uncertainty principle. Uncertainty in energy times uncertainty in time should be greater than certain constant, one constant. Which means that if you have a certain fluctuation in which you practically borrow energy out of nothing, and if that fluctuation lasts for a very short period of time, so that Heisenberg principle is not violated, then there's nothing wrong with it. So you didn't violate any conservation law in nature. So virtual particles are exactly that thing. So at certain moment, not at certain moment, all the time around us, you have fluctuations in which, for example, an electron and anti-electron, which is called positron, which is also a charged particle from electron, anti-particle of electron. So electron and a positron, they pop out of vacuum, but they meet very quickly and they annihilate and disappear again. So you can have such vacuum fluctuations at all energies. If that vacuum fluctuation is very high energy fluctuation, then it can live very short. If it is a very low energy fluctuation, so that uncertainty in energy is very small, such a fluctuation can live very long time. Which means that I have these quantum fluctuations at all frequencies, at all energies. Okay. So now imagine an experiment at which I put two parallel plates in a vacuum. So everything is evacuated. There are no particles there. I put it in vacuum. Now, if I have all of the possible wavelengths outside, so all of the possible frequencies, all of the virtual particles of any frequency that I can imagine, but in between the plates, I can fit only the standing waves. So only certain modes will survive inside. That would mean that outside I have much more virtual particles. Inside I have much less possible particles that I can fit in. There should be a pressure from outside towards inside, which means there is a less energy in between the plates than outside. So I showed you that there is an energy state which is lower than the vacuum. So if vacuum is at zero, then that lower energy state is a negative energy state. So in quantum mechanics, you can have states with negative energy and there is no problem about it. So that's why I said that at short scales, it's much easier to create a construct like a wormhole than on large scales. Because we do know in the real world, we've never seen anything like that. We've never seen macroscopic source of negative energy. But which again doesn't mean that some advanced alien civilization that's probably billions of years older than us, then probably they mastered the way of adding up, accumulating negative energy and so to macroscopic scales.
Because I read, I might have this wrong here, but to have a wormhole the size of maybe a meter long, you need the amount of negative energy, the worth of Jupiter's amount of negative energy to keep the throat open, which is a vast amount. And so, as you say, our technology needs to come on leaps and bounds before we're anywhere near that. So if we work on sort of Planck length sizes and microscopic, then we can hopefully get there.
I agree with you with one side note. Since this is still a domain of theory, we are still not quite sure. There are some papers, actually, pretty well-cited papers from well-known researchers, claiming that actually you don't need a huge amount of negative energy. A thin layer of negative energy should be enough. You put a thin layer of negative energy along the throat of the wormhole, and that should be enough to keep it stable. Since these are all theoretical considerations, before we make an attempt and build it, we don't know what's the correct answer. Do you need huge amount of negative energy or just a minuscule amount, like a thin layer of negative energy along the throat? I don't know for sure.
So my next question is, do you think that Kip Thorne's theory that an advanced civilization could pull a wormhole out of quantum foam and then enlarge it to classical size, do you think this is correct or possible?
Yeah, I think that's quite correct. And actually, if there are some macroscopic wormholes in the universe, I think that's the most plausible way to make them. I mean, for nature to make them, alien civilizations. Because in early universe, when quantum gravity effects at high energies, high temperatures, where quantum gravity effects are dominant, you can expect all kinds of topological defects to form, to change topology of space-time, so to create wormholes. And then if expansion of the space stretches them out, in particular inflation. So inflation can stretch them out and make them macroscopic. That's the most plausible way to make them.
Amazing. And so would this lead to quantum teleportation and quantum cryptography possibilities?
For quantum teleportation and cryptography, you don't really need a wormhole. I mean, you can use it for it, but you don't really need it. So quantum mechanics works, teleportation works, and quantum cryptography works pretty well without wormholes. But probably you're referring to that ER is equal to EPR proposal, where ER stands for Einstein-Rosen, which is the first wormhole solution ever derived by Einstein himself, and EPR, which is Einstein-Podolsky-Rosen, which is a synonym for quantum entanglement. So there is a recent proposal in which some reputable scientists propose that probably whenever two particles are entangled, quantum mechanical particles are entangled at large distance, a wormhole is created in between them. So that's a connection between general relativity, which is theory of space-time, with quantum mechanics. Because so far, as you probably know, we don't have a good theory of quantum gravity. So we don't know how to connect these two things. So people are trying many different creative ways to connect these two. So in that sense, yes. In that sense, yes. Yeah, you can use wormholes to explain entanglement, but even if wormholes don't exist, or if they don't exist between two entangled particles, entanglement will still work.
And so how does this link to string theory or even discovering, as you mentioned, a theory of quantum gravity?
As I said, we are really desperate in finding a theory of quantum gravity, because we can't answer our questions actually without that. We don't know what happens at the center of the black hole, where space-time becomes similar. We don't know what happened at the Big Bang, because we are entering the regime in which we need a quantum theory of space-time that we don't have. the best candidate that we have so far is a string theory. It's the base framework which can unify quantum mechanics with the theory of space-time. So there are many wormhole solutions within the string theory, just because it's a rich background, it's a rich framework. So, for example, in string theory, it may happen that you don't need a negative energy density because you have a lot of extra fields. You can have different membranes or branes in which we are located, and strings and all kinds of other defects. So in that sense, it may happen that you construct some very elaborate construct in which you don't need negative energy density, but still you need something. You need some external fields which are going to provide the same thing that negative energy density can, a repulsive force to stabilize the throw. In that sense, yes, string theory is a very nice framework and a very nice playground in which you can explore these effects. And as I said, string theory is currently the best candidate for quantum gravity, though I think we are still far from it. We have to change something radical. Yeah?
You can have like 11 dimensions, can't you, in the brane theory?
Yeah, either 26 if you believe in bosonic string theory, or 11 if you believe in supersymmetric string theory. So you have a lot of extra dimensions, so you have a lot of room there. The more dimensions you have, the more structures you have. The more structure, the more freedom, so you can play around.
So if wormholes existed, as in ER equals EPR, leading to vacuum polarization, then if this was near a singularity, could these effects lead to a punch through into another asymptotically flat region, effectively transforming a black hole into a wormhole?
Yeah, you touched another very interesting question. So the Schwarzschild solution, which describes black holes, it is singular at the center, at r equal to 0, at the very center. But we believe that once we learn how to quantize gravity, that singularity will be raised. Why? Because that's exactly what happened with electromagnetism. Electromagnetism has also 1 over r potential. I mean, the way electromagnetism works at the classical level is almost the same as the way gravity works at the classical level. The forms of electromagnetic and gravitational force, the forms are equivalent. The problem starts when you start to quantize. So what happened in electromagnetism? So because of that 1 over r potential, so when r becomes small, your force grows. At r equal to 0, force explodes, it becomes infinite, because you're dividing by 0. Therefore, atoms classically cannot exist, because you have proton and you have an electron, which is charged particle rotating around. Electron feels the Coulomb force, electromagnetic force of a proton, which grows the closer the electron comes in. So the electron, being an accelerated particle because it moves in circles, it will start radiating photons. It will start spiraling down, and that spiraling motion will accelerate because the closer you come, the force gets bigger and bigger. So it will spiral down in a fraction of a second. So electron classically cannot be in an orbit around the proton longer than a fraction of a second. So atoms cannot exist, but we all are made of atoms. So what happens? Quantum mechanics jumps in, tells you, okay, you have to give up describing your universe in terms of positions and velocities. You should describe them in terms of wave functions. You write down Schrodinger equation, which gives you dynamics, quantum mechanical dynamics. You solve it for an electron in an orbit of a proton. You see that the wave function for an electron around the proton is actually non-singular even when r is equal to 0, even at the center. So quantizing electromagnetism, you remove the singularity of the Coulomb potential, which is 1 over r. Now, we don't know how to do that for gravity, but we expect the same thing to happen. So the central singularity at the black hole, at the center of the black hole, will be raised once we learn how to quantize gravity. And then that singularity will be replaced probably with some very strong region with a region of strong gravitational fields, which is nevertheless finite. So there's nothing singular there. And it is very likely, I mean, not it is likely, I'm not sure if it's very likely or not, then that two asymptotically flat regions, meaning two disconnected spaces altogether, can be connected through the black hole, through the singularity. Singularity is removed, and you have a throat, wormhole throat, which connects these two regions. So yeah, that's quite possible to happen.
That's absolutely fascinating. Thank you very much. So my next question is, could humans traverse wormholes, perhaps in which the source of the weak energy condition violations required by the Einstein equations is the vacuum stress energy of the neutrino, or electromagnetic or massless scalar field, or even in a ultrastatic or cubical wormhole where, as you've touched on, the exotic matter is confined to a thin layer around the throat?
A small correction. So the stress energy tensor should not be from anything that we know, because neutrinos, electrons, positrons, blah, 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 they all have positive energy density. So it should be something new, some exotic matter that we don't know about, something outside of the standard model of elementary particles. But but it's interesting, as you said. So your question is actually, if humans can pass through, what will happen? Very interesting question, because general relativity doesn't forbid the closed time-like curves, which is that it doesn't prevent travel through time, basically. I mean, translated in plain English, you can travel through time. That means that along your trajectory through space-time, you can come back to some previous point where you have already been, or maybe you have never been. So you can go backwards in time, and there's nothing that prevents it from first principles. In order to prevent it, you have to put something extra on top of your theory. That's that chronological protection conjecture, that you're practically forbidding time travel, or maybe not forbidding, but saying that maybe I can travel through time, but I can only observe. I cannot change anything. People do that for a very practical reason. If I don't put that requirement on top of my theories, then I can construct a lot of paradoxes. One of the paradoxes is known as the grandfather paradox. So what if I go back in time and I kill my grandfather before my father was born? Then I'm never born, because my father wasn't born. Then if I was never born, then how did I travel back in time, and how did I kill my grandfather? So it's a paradox, obviously. Or the bootstrap paradox. Imagine that I'm an engineer and I travel forward in time to the future, future self. And I copy the patents that I filed in the future. I come back and I file them now. And I didn't steal anything. I copied them from myself, from my future self. But my future self has it because I filed them now. But I filed them now because I copied them from my future self. So how did I get these patents? Did I appear out of nowhere? So because of this paradox that we cannot wrap our heads around, the simplest way to deal with them is to say, okay, maybe I can travel back in time or forward in time, but I can't change the chain of events. So it can happen and I can't change it. But even that is not that bad, because then at least history will become an experimental science. Then, okay, I can't change anything, but I can travel back in history and see how the events really took place. I can witness them, I can change them, but I can verify that whatever I read in the books, in the textbooks of history, if that's true or not.
Yeah.
So in that case, it will be interesting.
And that would raise a lot of
It's a win-win situation.
That would raise quite a lot of ethical issues, because it might violate your privacy, and I'm sure there's human rights acts about this, and but it would also do a lot of good for sort of law and order, so seeing what actually happened, and there wouldn't really need to be a use for courts anymore, because you can go back and have a look at what happened, which would be, well, extreme. So I think it would completely change society. We will have changed by then anyway if we are doing this and we have the technology to do this, but it would really change the way we look at things.
Of course. And I mean, as you see, nature doesn't care about our moral codes or whatever, of our understanding of nature. Nature does whatever nature does. So if it's possible to happen, it will happen, we'll discover it. And as you say, it will change us. It's not, we can't say it's forbidden because we don't understand what will change or how it will change. So that's why I don't like this chronological protection conjecture, because it's basically saying just because I have no way to understand it, must be forbidden. No, nature doesn't work that way.
So we'll move on a little bit from wormholes now. So you've published a paper on the fact that as the length scale increases, new dimensions open up. And so how would this allow for some fundamental problems in cosmology, gravity, and particle physics to be attacked from a new perspective?
I hinted already, but let me expand. So the more dimensions you have, the more structures you have. But the more structures you have, the more problems you have. So so our proposal was, okay, what if there were no dimensions whatsoever? It's connected with the question, why do we live in 3 dimensions? I mean, 3 plus 1, 3 space-like and 1 time-like dimension. Mm-hmm. So why don't we live in 2 plus 1 or 4 plus 1 or whatever? Then we said, okay, probably at the very beginning, everything was frozen. So there were no dimensions excited whatsoever. Then at the Big Bang, the first dimension that got excited was time, because you need time for any dynamics. Without time, no dynamics, not in probabilities. So the first dimension that got excited was time. Then you excite 1 space-like dimension, then 2, then 3. So right now we are at the stage where 3 of them are excited. But in the future, when the universe is expanding on larger and larger scales, maybe we are going to excite the 4th dimension, 5th, and then eventually we may reach 10 or 11 as in string theory. But we are not there yet. So we keep expanding, temperature keeps dropping. So as the energy goes down, you keep exciting new and new dimensions. It's very connected with the fact that when you go backwards, at high energies, you lose dimensions. So you lose structures. You lose structures, you lose problems. So in 3 plus 1, we don't know how to quantize gravity. 2 plus 1, we do know how to quantize gravity. That was one of the big, of the serious motivations for this work. Another serious problem is the Higgs mass hierarchy problem. The Higgs particle that gives mass to other particles interacting with them, has problems on its own, because the Higgs mass is very sensitive to corrections, to quantum corrections. Because Higgs mass interacts with other particles too, so interaction with other particles will change the mass of the Higgs as well. If there is no new physics at the LHC scale, LHC is the huge collider at CERN, Large Hadron Collider. So if there is no new physics at the LHC scale, then interactions with other particles will drive the mass of the Higgs all the way to Planck mass. Then we don't understand anything, because Higgs can't be that heavy. Higgs has to be 125 GeV as measured at the LHC. But see, that's a problem only in 3 plus 1. In 2 plus 1, the Higgs mass is much less divergent. In 1 plus 1, it's not divergent at all. So hierarchy problem doesn't exist in 1 plus 1 dimension, 1 time-like and 1 space-like dimension. So at high energies, when you kill dimensions, when you shut down dimensions 1 by 1, you're shutting down your problems 1 by 1. And at the end, you are left with practically no structures. That's another way of unifying the whole physics. Because the way we are trying to unify different particles and interactions today is to say, okay, the strength of interaction, like electromagnetic, weak interaction, strong, and eventually gravity. So the strength of the interactions should unify at some very high energy scale. But even then, you have, in 3+1 dimensions, you have a lot of freedom. You have gravitons, which are spin 2 particles. You have photons, which is spin 1 particle. You have Higgs boson, which is spin 0. Then you have matter particles like quarks and leptons, which are fermions, spin 1/2. A lot of structure. But if our scenario is true, that you're shutting down dimensions as you are going back towards the Big Bang, you're shutting down the richness. So in 1+1, you don't have rotations. You can rotate in 1 dimension. For rotations, you need at least 2 dimensions, 3. But in 1 dimension, you can't rotate. No rotations, no spin. So you stop distinguishing between particles. For me, that's unification. So so when you start from the Big Bang, you have no room for diversity. So everything is the same. Then when you keep opening up dimensions, you keep opening up the room, you keep opening up complexity, and then you see all this diversity that you see around you. But when you extrapolate it back to the Big Bang, everything becomes the same. So for me, that's much more attractive notion of unification than unification of the interactions.
Absolutely, and it's really going to change the way we look at physics and change what sort of research we do in the future. And it's really important work that you're doing. So thank you very much.
You're welcome.
So in what way does this change the way we approach the cosmological constant problem? And how does it result in striking collider phenomenology or explain elongated jets observed in cosmic ray data?
Yeah, so as I said, theoretical motivation is manifold. So most of the problems that you can't solve in 3+1, not that you solve them, they disappear, they don't exist in lower dimensions. But now, what's the point? I mean, if it is just a theory, then okay, it's a matter of opinion. Or do you believe it or not? So you have to propose a way to test it. So we proposed a way to test it, and it's pretty simple to understand. So at the LHC, at the Large Hadron Collider, where we are colliding particles at high energy, if fundamental high energy physics is lower dimension, then the jets of particles, so when you collide 2 protons at the LHC, you produce a bunch of other particles and they come out in jets.
Yeah.
Jets are like cones, but the cone in 3 dimensions, the cross section is a circle. But if fundamental physics is lower dimension and your jet started propagating on a line or on a plane, and then at large distances it started branching out into 3D, then the cross section will not be a perfect circle, it will be an ellipse. If you see elliptic jet at the LHC, that's a strong indication. So elliptic rather than circular jet. Strong indication that fundamental physics happen on a plane, not in 3D. That's one thing. Another thing is coplanarity of jets. So in 3 dimensions, when you have 3 vectors, 3 jets, they are not on the plane. They're usually in space. They're not coplanar. So if you see coplanar jets at the LHC, that's unnatural for 3D. So coplanar jets would be again indication that the fundamental physics at a collision happen in lower dimensions, not higher dimensions. So that's one striking signature. Another one is gravitational waves. When LISA starts operating, the Gravitational Wave Observatory in space, it's actually a constellation of 3 satellites. And it will be very sensitive. It can probe primordial gravitational waves, which were produced in early universe. If our model is correct, that early universe had less dimensions, less than 3, then at certain point, the gravitational waves should stop. Because in 2+1 dimensions, gravity doesn't have propagating degrees of freedom. So gravity doesn't have gravitational waves. So in the early universe, at the Big Bang, there were no gravitational waves. When you transition from 1 to 2 dimensions, still no gravitational waves. You start producing gravitational waves when you transition from 2 to 3. Which means when LISA looks back, there should be gravitational waves at all frequencies and then cut off. At a transition dimensional transmutation, when you went from 2 to 3, gravitational waves should stop. Again, that would be a striking signature that something strange is going on. And finally, the first question that you asked about the cosmological constant. If we now continue this, so right now we opened up 3 dimensions, but at the horizon scale, at even larger distances, we open up the 4th dimension, 4th spatial dimension. Then you don't need cosmological constant. Then in order to explain the accelerated expansion of the universe, there is a natural solution of Einstein's equations without cosmological constant that gives you accelerated expansion of the universe. So see, that's why I was quite excited when we wrote that paper. Actually, it was a series of papers that with one simple idea that the number of dimensions is not fixed, but it's evolving with energy scales, practically removes the problems with the hand. You don't have to solve them. They just don't exist.
Yeah, that's absolutely brilliant. So we're going to move on to another paper which I'm going to link next to this podcast. So what is an electroweak star, and what equations did you solve for the possible existence for these?
To play with the stellar structure, you're solving Tolman-Oppenheimer-Volkoff equations. Again, general relativistic equations, but specialized for stars, for the dynamics of stars. So you're solving gravitational equations. Gravity plus whatever matter content you have. Radiation, matter, whatever. So what are electroweak stars? It's a new stage in evolution of stars. So let me just cut the story short, because the standard stellar evolution is pretty complicated. So you start with hydrogen gas at very low density, then gravitation pulls it together, then the temperature starts increasing at the core, at the center of that gravitational instability. Then when you reach whatever temperature which is needed for fusion, which is millions of degrees of Kelvin, then fusion starts. Then you are burning hydrogen into helium. Then there is a next phase in which you're burning helium into carbon, then carbon into higher elements, all the way to all the way up to iron. Exhaust all of that. There's many stages there. But when you exhaust all of the thermonuclear fusion fuel, then nothing to counteract gravity. So you can have a stable star. There is a gravitational collapse, and all of that stellar mass is compressed all the way down to about 10 kilometers. At that point, star is dead. There are no thermonuclear reactions, but there is something called Fermi pressure. It's a Fermi exclusion, Pauli exclusion principle that tells you that you can put 2 fermions together, 2 electrons, for example, together at the same state. So that pressure counteracts gravity for a while, and star can live in some equilibrium. That's like white dwarf. But if the original star was even more massive than white dwarf, and not even electron pressure, Fermi pressure, can stabilize the star, then you compress it even further. Actually, that's 10 kilometers. Neutron star is about 10 kilometers, and the neutron star forms when all of the electrons fall down to the cores of atoms. So electrons and protons combine and they make neutrons. So that star is made almost exclusively of neutrons. That's why it's called neutron star. But if the initial mass was even higher than that, then the QCD phase transition will happen, which means that QCD, that's quantum chromodynamics, that's the theory of strong interactions. So then even neutrons will be packed so densely together that you stop distinguishing between individual neutrons. You just have pure sea of quarks. Quarks are constituents of neutrons. Neutrons are made of 3 quarks. That's called a quark star. And so far, we believe that anything heavier than quark star there's nothing else to stop collapse. It has to become a black hole. So there's nothing after the quark Fermi pressure that can keep the balance with gravity. But then we said, okay, look at the standard model. So after QCD phase transition, what's next? Next, the electroweak phase transition. In electroweak phase transition, that's actually when Higgs gave mass to all of the other particles. It's a very important event in the history of our universe. Without electroweak phase transition, we don't exist the way we exist. So we know that it happened. So it's not a speculation. It must have happened. At huge densities, when you reach the electroweak temperatures at the core of a star, then electroweak processes kick in. In these electroweak processes, you can convert quarks, which you already have in your quark star. You can convert them into electrons and neutrinos. So now that's new fuel, new burning. Because burning in the sun, you're producing energy it's nuclear fusion, but the energy is produced in terms of very light particles, which are photons, which can propagate practically to infinity. Instead of creating photons, now you're creating neutrinos. Electroweak burning produces neutrinos. So it's a new source of energy. So you ignite a new source of energy, which can now support gravity even further than quark star. So it's a completely new phase in evolution that hasn't been explored so far. But as I said, it's not even a speculation, because you know that electroweak phase transition must have happened. So it's a standard model. So
that's fascinating. What's the sort of lifespan of these stars?
At least 10 million years. So 10 million years, see, it's much shorter than main sequence stars. Main stars like billions of years, tens of billions, or they are very light, even hundreds of billions. But the electroweak stars are about 10 million years, because that burning is very intense.
Okay. What is the possible connection of dark energy with the electroweak vacuor and collider phenomenology?
Yes, yeah, I like that paper very much. Yeah, that you just mentioned. I wrote a paper in 2008 about, okay, the electroweak phase transition that I just mentioned, that plays a very important role in modern high energy physics. We usually talk about the electroweak phase transition as something that has been done in early universe. So the phase transition happened, we are sitting at the bottom of the potential, which means there's nothing dynamical going on anymore. The electroweak phase transition is over, we are done with it, and we live in the universe as it is right now, which might have been true. But then in 2008, we said, okay, what if that phase transition wasn't over? What if that minimum in which we are sitting right now is not a true minimum, but actually there is a true minimum, which is even lower than that false minimum, since everything in nature tends to go to the minimum possible level of energy. Eventually, that would mean that we will tunnel through and end up in the true minimum. Of course, that would be a catastrophe for the universe, because the universe, as we know, would stop existing. But yes, some new life forms will form after that. What's interesting that we speculated, that's a pretty interesting possibility. And we speculated how to test it, how to know, how to check it in colliders and whatever. But that was 2008. And then in 2012, we discovered Higgs particle at the LHC. So now we measured the mass. So now we can reconstruct the potential. And when people reconstructed the potential, they said that's actually a very serious possibility. Still, we don't know for sure because of error bars, because of uncertainties in measurement. But it's there is very good probability that that picture is actually correct. That right now, today, we are not sitting at the absolute minimum of the potential. We are sitting at the false minimum, and there is a true minimum in which we will tunnel. We're not going to tunnel tomorrow or in 100 years. The lifetime is many billions of years, so we are safe, no problem about that. But still, it's very interesting that what we speculated in 2008 turned out to be the correct thing, something that was verified at the LHC.
Wow. So this is linked to this in some way, but can you tell us a bit about your work on dark energy and dark matter?
So I worked on both of these topics, dark energy and dark matter. But let me give you a disclaimer right at the beginning. I don't believe that we solved this problem. So there are many papers, not even hundreds, maybe thousands of papers on this topic. For sure, thousands. I don't think there is a good solution to these problems. We don't have good solutions to these problems, including my papers. So the dark energy problem is the problem of the missing mass in the universe. When you look at any galaxy or even galaxy cluster, you see that there must be something more there. You observe the orbits of stars, and then you see that these velocities have to be supported by more mass than we can see. So there must be some mass there that acts gravitationally, but we don't see it. And we call it dark matter. Dark energy is the fact that our universe is accelerating. So after the Big Bang, if you have only normal matter in it, the expansion of the universe should be decelerating because gravity is attracting. What we found in '98 is that instead of deceleration, actually we have acceleration. The universe is expanding faster and faster. So no normal matter can do it. So we have to put something that we call dark energy or the cosmological constant. So cosmological constant is the simple solution because it's only one number. You need something that is going to give you again repulsive gravity and push the universe apart. So I've written several papers on it. So for example, about dark energy, one of the proposals that I like, but I don't think that's a definite solution. The phase transition, again, we already have a period of accelerated expansion in the universe, which is called primordial inflation. So universe already went through the rapid expansion, superluminal expansion. And the most likely thing that happened at that time is a kind of a phase transition when some symmetry is breaking, and it's a violent event. So violent event in which the order of the universe is changing, and that can push the accelerated expansion of the universe. Since we already had it then, we thought maybe something similar happening right now, something violent. And what's that? Phase transition, some symmetry breaking. The only problem is that we broke all of the symmetries that we had. We're only left with electromagnetic symmetry, U1, that you cannot break, because if you break it, then photon becomes massive. So light will become massive. And the other one is QCD, SU3, color symmetry. QCD is quantum chromodynamics. So color symmetry, when it's unbroken, then quarks are confined in protons and neutrons, and we exist. If you break it, then gluons, particles which transmit the strong force, will become massive. Quarks will not be confined anymore; they will fly apart, and we will just disintegrate because we are made of protons and neutrons. So, if that phase transition is going on right now in the universe, it better be first order rather than second order. Phase transition is a smooth, continuous phase transition. First order is the abrupt, something similar to what I already spoke about, the electro phase transition. If we are sitting in a false vacuum, symmetry is still preserved there, so we live happily, nothing happens, but then abruptly we tunnel into a lower vacuum, and then everything changes. Quarks become deconfined, and then protons and neutrons decay. But as long as we are sitting there, we are fine. The universe looks just as it looks right now. And how do you explain cosmological constant? The amount, so what we call the false vacuum. So vacuum is greater than zero. So vacuum, what we thought was vacuum is not really vacuum. It had some energy density. That energy density is the cosmological constant. So that's the energy density that drives the accelerated expansion of the universe. So the good thing about that model is that it connects the cosmology, it connects macro universe with the micro universe. If QCD phase transition is ever going to happen, I mean, SU3 color symmetry is ever going to break again, that means that there must exist a new type of a colored scalar field, and that thing can be tested at the LHC. So the existence of a new colored scalar field outside of the standard model can be tested at the LHC. So if we ever find it, it's a strong indication that SU3 color symmetry could be broken in the future. So that's how you connect LHC, which is microscopic experiment, with cosmological observations, which is microscopic.
No.
About, yeah, say, yeah.
Sorry. Okay.
No, I was just going to say about the dark matter. Again, I mean, for time constraints, let me just tell you about the one of the papers that I wrote is about dark matter stars. There was a Cosmos survey project in 2006 that gave us a good distribution of dark matter and ordinary matter in some region of the sky. And then they pretty convincingly showed that since we have much more dark matter than ordinary matter, dark matter forms structures in our universe. And then ordinary matter just follows the gravitational potential wells, which are already formed by dark matter. Okay. Then we said, okay, but ordinary matter makes stars, galaxies, planets, and we are made of ordinary matter. Why not dark matter? So can't I have dark planets, dark stars, dark galaxies, whatever? And then we sat down and we calculated the best candidate for dark matter at that time was a particle called neutralino. But we showed that the annihilation cross-section of neutralino is higher than the elastic cross-section of neutralino. What does that mean in plain English? When these dark matter particles, so now you collapse them and you try to make a compact object out of them, they're going to annihilate much more efficiently than we thought. When they annihilate, the products are just photons, so radiation. Okay. If you try to compress them, they find each other, they annihilate, they get converted into radiation. So you can't make compact neutralino object. So that answers why there are no dark planets, dark stars, dark galaxies, or whatever. Right. With one caveat that if dark matter is something else, not neutralino, then maybe there are dark planets, dark galaxies.
That's absolutely fascinating. And so we're going to talk about your last paper. Well, last paper of today anyway. So how did you demonstrate that there is a maximal achievable temperature in a system where particles obey the laws of quantum mechanics and classical gravity before we then reach the realm of quantum gravity?
Yeah, that was the question that I asked when I was an undergraduate student, and I answered it many, many years. I mean, I wrote that paper maybe several years ago. So when I took a course in thermodynamics and statistical mechanics, I was kind of puzzled why there is a minimal temperature, so there is absolute zero, and you can't go below. There is no maximal temperature, so you can go all the way to infinity. And I wasn't happy with that. So, of course, it took me many, many years. So I sat down with one of my graduate students and we calculated the process. Okay, what happens when you keep adding temperature to the gas? So you have a gas with a certain number of particles. You keep heating it, putting heat in it, put energy. At a certain moment, you're going to start producing black holes because you're colliding two particles with huge energies. If impact parameter is the distance between two particles. That's impact parameter. If that impact parameter is smaller than the Schwarzschild radius for the given center of mass, Schwarzschild radius is the radius of a black hole. So if I collide them with huge energy and they come close to each other, then I'm going to produce a small black hole, microscopic black hole. Now, that small microscopic black hole will Hawking evaporate and it will disappear quickly. So you have to concentrate only on big black holes, I mean big enough so that they're colder than the gas, so that they survive in the gas, they don't disappear from the gas. And then it's pretty simple calculation, it's not even that difficult. You show that you can keep adding temperature to the gas, you can keep adding energy to the gas, heating up the gas, up until it reaches 10 to the 31 Kelvin. It's insane temperature, 10 to 31. It's very close to Planck temperature, but still lower than the Planck temperature. And at that moment, you have more black holes than particles. And then you can't raise the temperature anymore, because any more energy you put, you're putting energy into black holes, and black holes grow. It's not a gas anymore. So that's the absolute temperature that can be achieved in any conceivable experiment, 10 to the 31 Kelvin. So that was the result of our paper.
That's absolutely amazing. And so my final question, which moves on a little bit from the technical part, is that in a most recent paper you're working on, you explain that you are dissatisfied with the standard scientific approach and that you believe that we have to redefine what we call science substantially, expanding its framework if we want to make any serious progress. Why is this and what can be done?
It's not a paper, it's an essay, and I'm still not sure if I'm going to put it up out there. I mean, maybe. It's too provocative, yeah. So what's the problem? And it's observation that the last major progress we made in physics is 100 years ago, happened 100 years ago. Quantum mechanics and general relativity. So practically for 100 years, we are working within the framework of these theories. Of course, we made a significant progress, but that's an incremental progress. There is nothing revolutionary, there is nothing new. I can make even a stronger statement. The progress shouldn't, but okay, I go. So in the last 50 years, no high energy theories have made a significant progress. So 50 years. The last thing that we did, standard model and QCD 73 to 1973. Since then, thousands of papers, citations, conferences, whatever, we haven't found anything that's connected with nature. So nothing since early 70s. So that made me believe that probably we've picked with our way of thinking. So we hit the wall, that's it. We did everything we could with this way of thinking. Maybe we can solve a few remaining problems in the old-fashioned way, maybe. But for any significant progress, we have to redefine everything. We have to do something fundamentally new. Then I remember the book that I read maybe 20 years ago by the guy called Richard Maurice Bucky, who worked at the asylum for mentally ill patients. He observed consciousness at many different levels. So I liked very much what I read in that book. So he classified the different degrees of consciousness. He said, okay, even plants are conscious at certain level because they can, at the level of percepts. So they can feel if it is too hot outside. I mean, if it's raining, they open up the leaves. If it is too hot, they close up the leaves. So they operate at the level of percepts, and they are aware of their environment in a very primitive way. Okay, the next level are animals. They operate at the level of recipes. So he said, okay, a bunch of percepts tied together make one recipe. So dog, for example, or a cat, they can follow a certain recipe and they can do things. By processing information at the level of recipes, and one recipe contains a lot of percepts, they can process information much more efficiently than plants, obviously. Then he noticed, okay, dogs, for example, or cats, they're conscious, but they're not self-conscious. So dog knows, but he doesn't know that he knows. And separate dogs, animals, from the next level, which is humans. So humans, we know, and we know that we know. So we are self-conscious. Humans operate at the level of concepts. So a bunch of recipes that animals operate with, tied together, plus the correlations between them, make one concept. One word, one concept. That's why we have language. So whatever, love, I don't know, hatred, economy, whatever. So one word, one concept contains a lot of recipes and percepts in it. And because we are dealing with that bigger unit, we can process information much more efficiently than animals. Fine. But then he said, what's next? And he said, that's intuition. That goes beyond concepts. So what's intuition? Knowing the answer without going through all of the necessary logical steps. So you look at the problem and you know the answer. And he said, okay, that's next step in the evolution. So he claims that evolution, not claims, but that's his opinion, evolution is actually evolution in consciousness. So that's how the material evolved. That's how nature evolves. It's evolution in consciousness when we look from, I don't know, rocks and mountains, to plants, to animals, to humans. So he said that already many humans operate at the level of intuition. Like Einstein, I don't know, Nikola Tesla, Paul Dirac. So they would know the answer without going through all the necessary steps. So famous scientists, they work at the level of intuition. And he claims that more, though he lived like 120 years ago, he claimed that more and more people will, as the evolution is progressing, more and more people will start operating at the level of intuition until the whole human race goes to the higher level, and then everybody, just like monkeys, just like we, our ancestors. I mean, first, a few monkeys became self-aware. They became aware of themselves, and they started thinking in terms of concepts, and they developed language. The same thing now. A few bright people will, for example, you, will start operating at the level of intuition, and then sooner or later, the whole human race will transition to higher level. So I think that we picked with concepts. That's why we can't solve any fundamental problems anymore. So we are just accumulating problems, and there are no solutions for 50 years in my field. And I think we picked with concepts. We have to go to the next level. So we have to go with whatever you call it. I don't know how to call that new level of that new unit of processing the information that will contain a lot of concepts tied together, and now you are dealing with these units instead of individual concepts.
Well, hopefully my generation can achieve that, and we'll get there sometime soon. Yeah,
evolution speeds up. Yeah. More and more people will be at that level, and then we'll make a real breakthrough in solving not only problems in science, but everything is connected. I mean, world peace, world hunger, racism, I don't know, just name it. The way we are dealing with these problems right now, that doesn't work. Look at the pandemic around us.
Yeah.
We are struggling.
Yeah, but it's looking bright for the future.
Yeah.
So far, anyway. I agree. So that's all my questions. If you have anything else you'd like to expand on, or anything you'd like to ask me, or we can end it there.
No, I mean, you were pretty thorough, right? So you prepared pretty well. It was a very pleasant conversation.
Well, thank you so much for joining me today, and thank you everyone for listening.